Okay. Can you see my screen?
Yes, sir.
All right. So what we want to speak about, this new topic, is something called uniformly accelerated motion. Description of uniformly accelerated motion. This is the kind of motion we are interested in, and that's what we're going to be spending most of the time discussing during this course. If you are not speaking, please switch off your microphone. I can see Kelvin. We need that microphone off. Okay. Now, motion and movement of objects is an important part of life. Things are always moving around us, and we as people also do a lot of moving. So it is important that we are able to actually study, analyze, and also predict the movement of things. Scientists spend their time predicting a lot about how things move, whether those things are living things like animals or humans, or whether those things are planets like and stars or celestial objects. We do a lot of this thing, analyzing to see if you can come up with a formula. We study, and you also want to predict maybe when the next eclipse is going to come up and stuff like that. For starters, in our course, the kind of motion we are interested in is motion in a straight line, and also specifically, not just in a straight line, we are interested in this kind of motion, uniform accelerated motion. This is motion where there is something called acceleration. Okay? Acceleration occurs when the speed or the velocity of an object changes. When the speed or the velocity of an object changes, it can mean one of two things. Either that particular object you're trying to study begins to move much faster, so its velocity or speed increases, or it begins to slow down, meaning that the speed of that particular object starts to reduce until probably it comes to a stop. So that kind of motion where the velocity or the speed of an object is changing, it's not the same as time passes. That is what is referred to as accelerated motion. When there is acceleration, the speed of an object or the velocity of an object changes. It's not the same with time. When we talk about uniform accelerated motion, what we actually mean is that the acceleration is the same. Acceleration is a measure of how fast or how slow the velocity or the speed of an object is changing. If the velocity is changing very fast, then we say the acceleration is high. If the velocity or the speed is changing very slowly, then we say that the acceleration is low. So when we put a uniform accelerated motion, when we say uniform, it means that the value of the acceleration is the same throughout. The acceleration stays the same. If the acceleration stays the same, then it becomes possible for you to actually predict where an object is going to be after 5 seconds, what is going to be its velocity after 5 seconds, and how much distance it would have covered after that much. That's what uniform accelerated motion allows us to do. It's a simple case. It doesn't happen quite a lot, but there are certain things you can do with this simple case. Okay. Apart from, so in this, as we are looking at this uniform accelerated motion, there are two ways we're going to look at this issue. We're going to use graphs. So we're going to look at graphs which would describe this motion, and we are also going to use something called equations of motions. So we're going to come up with these equations from these graphs. They look like mathematics things, but they are not mathematics, because what they're describing is physics. So in physics, we use mathematics like expressions, okay, to describe our things. Once you have studied something in physics and analyzed it, we come up with equations, and that's something we're going to do a lot. We come up with equations which we're going to use to actually predict and analyze the motion of things. So that's what we are trying to do. That's what our objective is. When you're looking at when you're studying the motion of objects without consideration of what is causing the motion. So right now, in this topic, our concern is to describe the motion of an object, and we are particularly interested in this uniform accelerated motion. So we want to describe this uniform accelerated motion without looking at what's causing the motion. When you're doing this, when you study the motion of objects without studying the cause, then you're studying something called kinematics. When you look at what's causing the motion of an object, what's causing the acceleration, then you're looking at something called dynamics. So right now, we are going to look at kinematics. How do we describe the motion of an object? And that's the kinematics bit. Later on, we're going to look at the dynamics bit. What's causing the motion? Why does the velocity of an object change? What causes an object to change its velocity? So by the time we are done today, you should be able to describe what we mean by distance, displacement. These two are related. Speed, velocity, and acceleration. Basically, this is how we describe motion in terms of distance, displacement, speed, velocity, and acceleration. We're also going to see how we're going to use graphs to describe or to represent distance, displacement, speed, velocity, and acceleration. So it's possible for us to use pictures so that we can see what's happening. But of course, as you might be aware, this business of plotting graphs is very, very cumbersome. So yes, we can use it to show here and there, but normally we have got better tools to use. So we will not focus, we will show some things, but we will not focus too much on the graphs. And the course also shows you how to use these graphs, but the focus is not really on graphs because graphs are very cumbersome to deal with. They are time consuming, but at the same time, if we look at motion, mostly what you're interested in is acceleration, the velocity, the speed, the displacement. These things can be found much faster by using other methods. Why do we need a graph? For example, there's a graph called a velocity time graph. So we're going to see how from a velocity time graph, when we work out the area under this velocity time graph, we can get the displacement or the distance which has been moved. Also, from the velocity time graph, we're going to see how we can determine the acceleration from the gradient of the velocity time graph. So the gradient of the velocity time graph gives you the acceleration. There are other types of graphs which we can look at, but the most important ones, the most important graph in physics, motion graph, is a velocity or a speed time graph, because a speed time graph shows you how the speed of an object is changing after every second. At the same time, you can also work out from a speed time graph or velocity time graph the distance which has been moved from the area under the graph. So the area under the graph corresponds to the distance or the displacement which has been moved, and also the slope at a particular point represents the acceleration. So we're going to see what these things are. So the first thing we're going to look at when you're talking about motion is the length which has been moved by an object in a certain amount of time. So the length moved by an object, that's what we refer to as distance or displacement. In the case of distance, which is denoted d, distance is a scalar. It does not have direction. So if you move a distance of 100 meters, that's how much length you have moved. If an object moves a distance of 100 meters, or you run a distance of 100 meters, that's how much length you have covered. That's what we call distance. There is no information about the direction in which you're running. So distance does not have direction. It has got size, but no direction. Distance is a form of length which has been covered or moved by an object in a certain amount of time. Are we clear? Distance is a form of length covered by an object. It is a scalar, meaning that it has got size but does not have direction. On the other hand, displacement is a distance in a specific direction. So you cover a certain amount of distance, but you also need to tell us in which direction this distance was covered. For example, here you have an object which moves or covers a displacement of 120 meters west. How much distance was covered? 120 meters. In which direction? West. This, when you're given this information, 120 meters, the size, west is the direction. What you're talking about here is displacement. If you're just given 120 meters, then we are talking about distance. Are we clear on what distance and displacement are?
We are clear, sir.
Yeah. Yes,
The
sir.
next quantities we're going to use to describe this motion is speed and velocity. Speed is a measure. These two are related also. Speed and velocity are related. One of them is a scalar, the other one is a vector. Speed is a scalar, meaning that it has got size but has got no direction. Velocity is a vector, meaning that it has got size and direction. Now, speed measures how fast you are covering distance. Speed is a measure of how fast you are covering distance in a system. So basically, you cover a certain distance, then you divide that distance by the amount of time it has taken you to cover the distance, so that we know how much distance did you cover in a second. That is speed. Velocity, on the other hand, is speed in a specific direction. Velocity is speed in a specific direction. Velocity is a vector. In other words, velocity is how fast you are covering displacement. How much displacement and in what time did you cover this displacement? So you divide the displacement divided by the time. Are we clear on the distinction between speed and velocity? One is a vector, the other one is a scalar. Speed is a scalar. Velocity is a vector. Speed is a measure of how fast you're covering distance. Velocity is a measure of how fast you're covering displacement. Is that clear? Speed in a specific direction, that is velocity. So if you're covering, this is how fast you're covering distance. You're covering 150 meters per second. You don't tell us in which direction you're going or who is chasing you. You're just saying, I just ran into the darkness. I don't even know which direction you're running. You just ran because you're scared. Or maybe there's a police. They say, hey, stop. Then you just started to bolt and run. That is speed, because you don't have information about the direction in which you're covering this distance. On the other hand, if you tell us you're covering 150 meters per second east, this is not speed but velocity, because there is information about direction. Are we clear?
Yes, sir, we are following.
Okay. Now, there are two types of speed or velocity which we are interested in this course. One of them is something called instantaneous speed or velocity. Now, who is that? Emmanuel Zolo, can you switch off your microphone? So there are two types of velocities or speeds you're interested in. One of them is called instantaneous velocity or instantaneous speed. This instantaneous speed or velocity is an estimate of what the speed or the velocity of an object is at a particular point in time. When the police set up a speed trap, then at the speed trap they catch you, they say you're driving above 60 kilometers per hour. At that, it doesn't matter whether before then you're driving at 20 kilometers per hour or you're driving at 40 kilometers. At that particular point when they catch you, your speed was above the speed limit. Maybe you're driving at 70, you're driving at 80, most people drive at 100 kilometers per hour. So at that particular point in time, what is your speed? That is what is referred to as instantaneous speed or instantaneous velocity. So we are interested in this kind of speed. The problem with this kind of speed, instantaneous speed or instantaneous velocity, is that your instantaneous speed or velocity is going to change after every second. Okay, maybe there's a car in front, you slow down, so your speed changes after every second. When your speed changes after every second, it means that those of us who are trying to study your movement or your motion have a lot of values. We have a lot of numbers to work with. Okay? When you have a lot of values of speed, at 1 second this was the speed, at 2 seconds it is this. When we have a lot of values to work with, the job of trying to study and analyze and predict your movement becomes very difficult. So instead of focusing on this instantaneous speed or velocity, there is also another kind of speed which we focus on, something called average speed or average velocity. Using all these values you have, different values of speed, we can come up with one value of velocity which we can use to describe your movement. Okay? So average speed or velocity is another kind of speed which we use. This is just one value. Most of the time, the average speed of velocity actually might not even be one of the speeds, instantaneous speed values an object had. Okay? It's just that we are being lazy and we need to find a way of describing your movement in terms of speed. So if you have got all the time in the world, you can focus on the instantaneous speed of velocity, but even the police don't have all the time in the world to follow up what your speed is everywhere in Osaka or wherever you are. Okay? The police are only interested in what is your speed in certain locations. Say in this location, near the school, you're supposed to drive at 20 kilometers per hour. But when they were there, you were not driving at 20 kilometers per hour. It doesn't matter whether before you came to that school, you were crawling or walking. No. Okay? So, an object which is moving produces a lot of values of speed, especially instantaneous speed. These values are too much for anyone to handle. So basically, it's cumbersome business and we're not really interested in following up things so much. The only kinds of instantaneous speeds of velocity we're interested in is something called the initial speed or initial velocity and something called the final speed or final velocity. The initial speed or initial velocity is the speed of an object the moment we become interested in it. And the final speed or final velocity is the speed of an object the moment our interest in this particular object ends. So if we start looking at an object, then we say we're going to look at this object for 10 seconds. So the moment we start looking at it, then we get what is its speed. That speed which it has when you start looking at it, that's what's called the initial speed or the initial velocity. After the 10 seconds, we look at the object again. We look at what the velocity is or the speed is. That's the final speed or the final velocity. In between these 10 seconds, the object could have had other values of speed or velocity. We are not interested in those because it's too much information. Are we clear?
Yes, sir, very clear.
Yes, we are not interested in values of speed or velocity during the time we are measuring. We are only interested in the speed or the velocity of an object at the beginning or at the end. The police might be interested in what your speed is anywhere, especially where they are, where they have mounted a speed trap. They might be interested. In our physics course, we are not interested. We are only interested in the speed or the velocity the moment we start measuring the time, when we switch on our stopwatch, and the moment we stop our stopwatch. So the moment we begin measuring time, what is the speed? The moment we end the time, what is the speed? Then during this whole time, when the speed was whatever it was, which I don't want to know because I'm not interested, there is this thing called average speed. We can describe whatever happened in between here using average speed. Average speed is an estimation. We're trying to estimate what we think happened. That estimation might be closer to what really happened. At the same time, it might not be. It might be far from reality, but physics people, we try to find a way of simplifying things as much as possible. So we want you to be aware of those two things. What is instantaneous speed or instantaneous velocity, and what do we mean by average speed and average velocity? Instantaneous speed or velocity, you can get what the speed is using those speed trap things which the police use to measure what the speed of a car is at that particular moment. So you get that using instantaneous speed. Average speed or velocity, you can get it differently. Average speed, how do you get the average speed? Average speed is equal to the total distance covered divided by the total time taken. That's how you get the average speed. So you just look at how much distance has been covered and how much time did it take to cover this distance. That gives you your average speed. Are we clear? Whether when you're covering this total distance, you stopped to pee or to go to the toilet, we don't care. We're just interested in how much distance you cover and in what time, or you're eating ice blocks or whatever it is, we don't care. Our interest is in the distance, the total distance covered divided by how much time it took. That is going to give us what we call average speed. So it doesn't tell us whether you hit into a speed bump, or there was a pothole, or the road was very smooth, you're moving faster. Average speed doesn't have such information. The total distance covered is measured in meters, units of meters. The total time taken in seconds. So average speed has got units of meters per second. There is also average velocity. Average velocity is defined as the total displacement covered divided by the time taken. Again, we are not interested in specific values of the velocity of this particular object at 2 seconds, at 3 seconds, at 4 seconds. We are not interested. We just want to find out what was the total displacement and how much time did it take. Are we clear? Are we clear?
Yes, sir.
We can
Yes,
find.
we're clear.
We can find. Okay. We can also find the average velocity as follows: half initial velocity plus final velocity. So when we the speed of an object when you start measuring the time, that's the initial velocity. then the speed of an object when you finish measuring the time, the final velocity. So we get this initial velocity is instantaneous velocity. Initial instantaneous velocity plus final instantaneous velocity. When we add these two, you add your initial instantaneous velocity plus your final instantaneous velocity, then you divide them by 2. What you get is also average velocity. So you can use the value of the speed or velocity when you started measuring, and when you finished measuring, you add them, then you divide them by 2, you're going to get your average velocity. The average velocity you're going to get is the same. So average velocity, we love average velocity because it's just one number, and we use this number to compare who was moving faster and who was moving slower. Depending on the average velocity, if your average velocity is higher, we'll say, oh, this object A was moving faster than object B based on only the average velocity. So at least there's one thing we can do, and comparison you can do, which objects were moving faster than the other ones based on only the average velocity. We have an example here. It says an athlete takes 10 seconds to run a distance of 100 meters. Calculate the average speed of the athlete during these 10 seconds. So the distance covered is 100 meters and the time is 10 seconds. So the average speed in this case, is going to be equals to the total distance, which is 100 divided by the total time taken, and that's a formula d divided by t. So you've got 100 meters divided by 10 seconds. And basically the average velocity or speed is 10 meters per second. Now, when you look at this average speed or velocity of 10 meters per second, you might be misled to think that this guy was covering 10 meters after every second. So you might think in the first second he covered 10 meters. Then in the second 2 he covered another 10 meters. So that becomes 20. The third second he covered another 10 meters. That becomes 30. So at the end of 3 seconds, this guy covered 30 meters. Like that, until all the 10 seconds were finished. However, if you have actually done any bit of running, you know that that's not how people run. Because when people are running, they start off slowly, then they gain speed, then they slow down. If you haven't been running, or you watch running, for example, how Usain Bolt used to run, he would start off slowly, then run very fast and slow down. So if this calculation is saying that this guy is covering 10 meters per second, this is not true, because no one runs like this, not even a robot. Is that clear? In reality,
Very, very clear.
yes, in reality, there is no one who runs like this, covering 10 meters after every second. No one does that. Okay? So, average speed is describing something. Yes, at some point, maybe as this person is running, they might be able to cover 10 meters per second, maybe once or 2 times and during the course of their running. But most of the time, when we work out the average velocity or the average speed, we are trying to find a number to describe what is happening. Sometimes the average velocity or the average speed is very far away from what actually happened, far from reality. As much as it might not be real or reality, a true reflection of what happened, it is a very, very, very important physical quantity, because as you can see, our average velocity actually gives us a connection between the initial velocity and the final velocity. So there are other physical quantities which are related to this average velocity. So as much as, yeah, it's a bit too imaginative, but yeah, we use it a lot. Okay. The other thing we're interested in is something called acceleration. Now, acceleration refers to how fast the speed or the velocity is changing. That's what acceleration is. It's how fast the speed or the velocity is changing. If the speed is not changing, then there's no acceleration. The change in speed can be an increase, the speed or the velocity can increase, or the speed or velocity can decrease. Okay? And what we are interested in is something called average acceleration. So, over a period of time, we want to find out what is the average acceleration. The acceleration at any particular point can be different, but what we are interested in is the average. And how do we get the average? Basically, it's a change in the velocity or speed divided by how much time has taken. And how do we work out this thing? We use the final speed of velocity minus the initial speed of velocity divided by how much time it has taken. This is how we work out the average acceleration. Average acceleration is equal to the final velocity or final speed minus the initial speed of velocity divided by how much time it has taken. This v for final velocity minus u for initial velocity divided by time. This v minus u is the change in velocity, which is measured in meters per second, divided by the time, which is measured in seconds. So you end up having your acceleration in units of meters per second squared. So acceleration measures how fast the velocity of an object is changing. That's what acceleration does. It measures how fast the velocity of an object is changing. So if the velocity is changing very slowly, then the value of acceleration is going to be small. If the velocity is changing very fast, then the value of acceleration is going to be large. Here we have an example. A car accelerates from rest to 28 meters per second in 10 seconds. Calculate the average acceleration the car experiences. So, the velocity of the car, when it's at rest, the velocity is, its initial velocity is 0 meters per second. That's u. And the final velocity of the car is 28 meters per second. That's v. Then it does this change in velocity in 10 seconds. So we have all the information we need to work out the acceleration. Remember, the average acceleration here, the final velocity minus the initial velocity divided by how much time. So the final velocity is 28 meters per second, the initial velocity is 0 meters per second, divided by the time it takes to make this change. So that's going to be this. A is equal to v minus u divided by t. V is 28 meters per second, u 0 meters per second. The time taken is 10 seconds. So you end up with that 28 meters per second on top divided by 10 seconds. We end up with a value of acceleration, which is A equals to 2.8 meters per second squared. So we have a number, 2.8 meters per second squared. That's the acceleration. What does it mean? It means that the velocity of the car increases by 2.8 meters per second every second during this 10 seconds. That's what acceleration means. If we give you a value of acceleration as 2.8 meters per second squared, it means that the velocity of this car increases by 2.8 meters per second every second for the next 10 seconds. And here we have a table. T, time in seconds, then V, the velocity meters per second. So here we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are the 10 seconds of the car. And the velocity will be increasing by 2.8 meters per second. So when the time is 0, the velocity is 0. Then when the time is 1, the velocity increases by 2.8 meters per second. Now it becomes 2.8. When we've got 2 seconds, it will increase by another 2.8, so it will be 5.6. 3 seconds, it increases by another 2.8. From 5.6, now we end up with 8.4. 4 seconds, that's one more second, it increases again by 2.8. Now it becomes 11.2. After 5 seconds, it increases by another 2.8. It becomes 14 meters per second. After 6 seconds, it increases by another 2.8. It becomes 16.8. Then you've got after 7 seconds, it increases by another 2.8. It becomes 19.6. After 8 seconds, it increases by another 2.8. It becomes 22.4. Then after 9 seconds, it increases by another 2.8. It becomes 25.1. After 10 seconds, it increases by another 2.8 to become 28. So this is an estimate of what we think happened using acceleration, using average acceleration. We think the velocity of this car was increasing by 2.8 meters per second. However, you and me did not see this car. So we don't really know exactly whether this is what happened. What we have just been given is information to say it started from rest and it reached 28 meters per second in 10 seconds. Maybe something else happened. But based on this information, we are trying to analyze and predict the movement of this car to say, okay, the most logical thing which could have happened could be this. Are we clear?
Yes, sir.
We didn't see this car. We didn't see this car.
Yes.
We didn't. So we are trying to estimate what we think happened. To say, based on what we have, the initial velocity, the final velocity, and how much time, we think this is how the velocity increased. That's what acceleration means. When you say you have an acceleration of 2.8 meters per second squared, this is average. We are saying we think the velocity was increasing by 2.8 meters per second every second. Any questions?
May you repeat instantaneous?
No questions, sir.
Is it instantaneous velocity the network at this scheme?
Instantaneous velocity is what the police are interested in. Instantaneous velocity is the speed of an object at a specific time. That's what instantaneous velocity is. Instantaneous velocity is the speed of an object at a specific time. The police are interested in that. The only kind of instantaneous velocity we are interested in is the initial velocity and the final velocity. Initial velocity is when we start measuring this 10 seconds. This instantaneous velocity. This U is an instantaneous velocity. That's what we are interested in. When we start measuring the 10 seconds, then the velocity of the car at the end of the 10 seconds, this 28 meters per second, that is another value of instantaneous velocity we are interested in. So we are not interested in everything else in the middle here. What we are interested in is at the beginning when you start measuring, what is the instantaneous velocity? 0 meters per second. At the end of the 10 seconds, what is the instantaneous velocity? 28 meters per second. In between here, what we have done, this 2.8, 5.6, 8.5, 11.2, 14 meters per second, 16 meters, this is all pure guesswork. These velocities here, these 2.8, 5.6, 8.4, 11.2, 14, 16.8, 19.6, 22.4, 25. This is all pure guesswork. But this is guesswork which is based on good thinking. We think this is what happened. So we are not just guessing blindly. Okay? We are doing guesswork, yes, but this is good guesswork, and usually things turn out that we are, in physics, we are more correct. Our guesswork works. It's not just guesswork which doesn't work, like wildly guessing, stuff like that. Are we clear?
Yes, sir.
Okay. Now, this table which you have here can be presented in terms of a picture. This picture here. The values of time, we have got 0 up to 10 seconds. Then on this side, you've got velocity values. So we can plot the values of time and velocity, and when we do that, we end up with this nice graph. This is a picture representation of what we think happened. We think the velocity was changing like this. Maybe that's not how the velocity was changing. Maybe there was a pothole in the road. But you don't know because you're not there. Or maybe there was a hump. Are we clear? So reality might be different from what we think happened. But we are saying, okay, we're imagining the road was very smooth, there were no potholes, it wasn't raining, there were no police, so the car was moving like this. Okay, so this is what we think happened. That's why in the physics and the business of predicting, it's not that this is how things happen. No. We have come up with the thing, so we think this is what happened. So we have the velocity this side, on the y-axis, you've got this on the x. So this graph, which shows you how the velocity was changing, how we think the velocity was changing, and versus the time, this is what is called a velocity time graph. From this velocity time graph, if we work out the slope, we pick any points here, any 2 points, which are fairly separated. We pick any 2 points, then we work out the slope or the gradient. We draw a straight line between that. We work out the slope. The slope or the gradient is going to be the change in the velocity divided by the change in time. So you pick 2 points, then you work out the slope. Here I've picked V8 and T8 and V3 and T3. So the third somewhere there, and basically that's going to be the V8 is 22.4. So I've picked this point, 22.4, this one, the velocity of 22.4, and a time of 8 seconds. Then I think the another one is this one, 3 seconds and 8.4. So I pick those 2 points. Then I work out the slope. So the change in velocity is going to be 22.4 meters per second minus 8.4 meters per second. Then at the bottom, 8 seconds minus 3 seconds. So on top, I'm going to end up with 14 meters per second. Then at the bottom, I've got 5 seconds. Then 14 meters per second divided by 5 seconds, I get this. 2.8 meters per second squared. That is the slope or the gradient of the line. This 2.8 meters per second squared is the same as this acceleration which you found here. 2.8 meters per second. That's why we were saying earlier to say, you will see that the slope or the velocity, the slope or the gradient of a velocity time graph gives you the acceleration. Are we clear? When you have a velocity time graph like this, then you work out the slope of the line. That slope of the line is actually in reality equal to the acceleration of that particular object. Are we clear?
So yes, sir, we agree. One more.
We are saying that the slope of a velocity time graph is equal to the acceleration of the object. So when we give you a graph of an object which is moving, say, no, this car was moving somewhere, and this is a graph of the object. We show you a velocity time graph. Then we ask you to say, what was the acceleration in the first 10 seconds? Then you look at the 10 seconds here. Then you work out the slope of this line, of these, as you can see, these points lie on a straight line. Then you work out the slope. That slope is equal to the acceleration of the object. Are we clear?
Let's say, since you say,
Huh?
since you say change in acceleration is velocity. So let's say the car was moving at an acceleration of 30 meters per second squared. Then
Acceleration of what?
constant. Yes. Then
This-
at some point it was constant. So does that mean the velocity won't change to be zero, or it will also be constant?
Look at this graph. Look at this graph. Before you say velocity won't change, what are the values of velocities here? Are they changing or not changing? This is velocity this side. Is it staying the same? When you're dealing with acceleration, the velocity has to change.
Increasing.
When you're dealing with acceleration, the velocity has to change. We are not interested in any kind of motion where the velocity is not changing, because it's boring, because you can predict anything. We are interested in motion where the velocity is changing but the velocity is changing in a predictable manner. Okay, it's increasing by 2.8 meters per second every second. That's where the predictable manner comes in. How fast the velocity is changing always during this time, we are assuming that the velocity is changing by 2.8 meters per second every second. So it's increasing by 2.8 meters per second every second. That's why as the topic says, description of uniform. When something is uniform, it means that something is the same or it's constant. Uniform accelerated motion. So throughout these 10 seconds, our assumption is that the velocity, the acceleration is the same. But that might not be true, because if you see a big pothole, you are still not going to increase the speed. You slow down. Or if you see a pothole, a hump, you slow down. Or if a traffic light turns red, you slow down. If a policeman jumps in front of your car, you are going to slow down. Or if you see a cow move in front of your car, you are going to slow down. So it's not true that in the reality you can move at the same acceleration. There are so many things which can happen which will force you to change the acceleration very fast or very slow, or depend. Anything can happen. Are we clear?
Yes, sir.
Yes. Yes, actual motion itself. Actual motion is more complicated than what you're trying to do here. We are trying to make things simple as if that's how simple they are. No, that's not how simple they are. But even with this simple way of describing things, we can actually get some very good results. Okay, the next thing we want to do is the area under this graph. As you can see, from here, like that, then this way, that is kind of a triangle. And the base of the triangle is from this side up to there. So the base of the triangle is measured in units of time, 10 seconds. And this height of the triangle is also measured in units of change in velocity. The height of this thing, you could say, is 28 meters per second. So if you work out the area of the triangle, area of a triangle is equal to half times base times height. The base is 10 seconds, the height is 28 meters per second. When you do this, half times base, 10 seconds times height, when you do this, you get this. You get a physical quantity which has got units of length, 140 meters. This 140 meters is telling you that when you work out the area under the velocity time graph, what you get is a distance or a displacement. In this case, the displacement. So the area under a velocity time graph gives you displacement covered by an object in that time. Of course, there are these other graphs you can look at, how the displacement is changing, like that. We are not really interested in this kind of graphs, but it's fine, you can look at it. And also how the acceleration changes. The acceleration is constant. That's why it's called uniform accelerated motion, and how the velocity falls if you did the other way around like that. And also how it would fall like that. We are not interested in the other graphs. The only kind of graph we're interested in physics, when it comes to motion, is the velocity time graph. This one shows you what happens if the acceleration is positive. If the acceleration is positive, it means that the velocity increases. This other graph, this other velocity time graph, shows you, this one, what happens when the acceleration is negative. When you've got a negative acceleration, it means that the velocity of an object is going to reduce as time passes. So an object basically slows down. Whenever you've got negative acceleration, the velocity of that particular object slows down. Are we clear? Between positive acceleration and negative acceleration.
Well, yes, sir.
Okay. Yeah. So even here, you can still work out what is the slope and also what is the area under the graph, like that. You can choose to work out different areas under the graph, different trapeziums. They will give you how much. For example, if you're interested in finding out how much distance was covered between here, how much distance was covered between 2 seconds and 5 seconds, you would work out this area from here up to there. Then you come down like this up to there. So you work out what is the area of this trapezium. This area of this trapezium is going to give you what is the distance which was covered between 2 seconds and 6 seconds. Are we clear?
Yes, sir, we are.
Yeah. Unless there are any questions for this bit, we come to the end. We must finish here. So the next class is going to be tomorrow.
Sir, I have a question, sir.
Yes.
You said the slope of the graph is the acceleration. What about the average acceleration?
What?
You said the slope of the graph is the acceleration. It's equal to
It is the average acceleration. It is the average acceleration.
Or it is the same as the average acceleration?
Yes, it's average acceleration.
Okay, thank you, sir.
All right. Any other question?
Excuse me, sir.
Yes.
Was the lecture being recorded?
Yes, it's always recorded.
Thank you.
Okay, so we're going to upload it to YouTube. Now, before we leave. So that you can, those of you who want to watch again, you can watch it again.